Hello everyone. My name is Aarav Ratra. I am currently doing my B.Tech in Engineering Physics from IIT Roorkee. And today I will be presenting the experiment speed measurement using an electromagnetic transducer. This experiment is a part of the course PHN 310 Applied Instrumentation, which aims at employing various principles of physics to industrial as well as daily applications. Okay, so now let's get on to the experiment. The aim of this experiment is to study the performance of an electromagnetic pickup as a device to measure the speed of a DC motor. This experiment utilizes an electromagnetic pickup which is used as a proximity sensor to measure the RPM of a motor, and it utilizes the principles of electromagnetic induction. Okay, now let's have a quick look at the apparatus. The apparatus consists of the following units. First, we have our speed measurement trainer kit, which basically acts as a signal conditioning unit for the sensor input. We have got a motor with a slotted disc having 15 teeth and powered by an adjustable power supply. We've got an electromagnetic pickup which is fitted near the disc. We have got a multimeter to display the motor voltage, as well as an oscilloscope to view the signal through various stages of conditioning. In this particular attempt at this experiment, we have used a digital storage oscilloscope. Otherwise, even a cathode ray oscilloscope is also popularly used. Okay, so now let us briefly go through this trainer kit. There is a power supply for the motor, and the sensor input is connected through the wave shaper, and a multiplier which basically do some signal manipulation, as well as a counter to register the number of pulses per second, and which is operated with a 1 Hz clock, and a 7 segment display. So we will go through them in more detail when we are doing the theory. Okay, so let us have a quick look at the construction. We've got our pickup here. This consists of a central magnetic pole piece and also a pickup coil. So whenever there is a movement of the disc, there is a change in the magnetic flux which induces a current in this pickup coil. So based on this principle, we can register the proximity of the tooth. Okay, so for a rotating disc, we will employ this logic to measure the number of times there is a tooth near the pickup to measure the RPM and the speed, as the pickup will give an oscillatory output and the number of pulses can be counted. So in the disc we have 15 slots, so the sensor would basically give an output of 15 pulses per single revolution, okay, which is written right here. Now what happens next? So now the output signal is fed into the wave shaper circuit. Okay, so what this unit basically does is that it converts the input signal to a square wave, and the square wave is easier to work with. So the output from the sensor which we actually receive, the raw output, it is not exactly sinusoidal in nature but somewhat similar in shape. Alright, it is like this. But the wave shaper basically converts it into something which looks similar to a square wave. The wave shaper can be employed using various means. We can use amplifiers and clipper circuits as well. But for our purposes, it just converts it into a square wave. We will not be getting into detail about how this works. I just gave an example. Okay, now the next unit which we see here is the multiplier. Okay, now what does the multiplier do? It basically multiplies the frequency of the output of the wave shaper by 4. Hence, we have 15 into 4, which is equal to 60 pulses per revolution. Okay. Now, how does this multiplier work? It generates harmonics of the input frequency, and we use bandpass filters to basically filter out the unnecessary frequencies, and we obtain the desired multiple. Okay, so in this case it multiplies the frequency by 4, giving 60 pulses per revolution. Okay, then we have our counter. Okay, what this basically does, it receives the number of counts in 1 second. It measures the number of counts received in 1 second, and hence it is operated using this 1 hertz clock. Alright, and the number of counts are displayed on the 7 segment display. So the output displayed is the frequency of the multiplier in hertz. Alright, that is pulses per second. Now 1 RPM corresponds to 60 pulses per minute, which is nothing but 1 pulse per second, which is nothing but 1 hertz. So the motor RPM magnitude will be equal to the frequency multiplier. I mean the frequency of the multiplier output. Okay. So this was the operation in the RPM mode. We can also discuss the operation in the speed mode. Alright. So what we do is that we can switch the RPM/speed switch right here. And then we can manually measure the counts directly by using the push to count button. And we can measure the time manually as well using a smartphone or a stopwatch, and hence we can use that to obtain the number of counts per second, and hence we can use that to obtain the speed. Okay, so alright, so as you can see here, we take into account that one pulse corresponds to pi d by 15 distance traveled, where d is the diameter, which is 85 millimeters in this case, and hence we can use that to measure the speed sort of manually. Alright, and we also have a relation between the RPM and the speed, and we can use both means, the RPM mode as well as the speed mode, to obtain the speed of the motor. Now here is a quick demonstration of the experiment. Alright, so this is the speed measurement trainer kit, which uses an electromagnetic pickup. The circuit has already been described previously, so I'll be focusing on the other things here. So this is our DC motor with a slotted disc, alright, and this is the electromagnetic pickup, which is basically doing all the magic. And this circuit is connected to oscilloscope via a wave shaper right here. We also have a multiplier circuit as well. So whenever there is any rotation here, that is caught by the oscilloscope. Okay. So now this DC motor is powered by a power supply, and now we will be increasing the power supply. Uh, there will initially be some inertia, so only after a threshold it will begin to rotate. Okay, it has begun to rotate, and the voltage right now is 1.87 volts. Okay, and here the wave shaper, it has a frequency of 100, and it's fluctuating, but it's roughly 150 hertz. Okay, and now we connect it via a multiplier, which multiplies the frequency by 4. This gives a frequency of about 610 hertz or so, which matches with the display RPM which is shown on the counter. So we take a note of both the wave shape and the multiplier readings, and hence we get an idea of what the RPM of this motor is. Okay, so I hope you enjoyed. So we note down this reading. We observe that the voltage here is 1.87 volts, and the wave shaper frequency is obtained to be roughly 150 hertz, and the multiply frequency comes out to be roughly 610 hertz. The display RPM is 617 rotations per minute. We can observe some error here, but the oscilloscope's frequency actually fluctuates like a lot, alright, because it uses a different means of measuring the frequency. But what is actually important is that the two quantities here are almost equal. But moving forward, we will be trusting the display RPM more, because it is measured internally in the circuit. Okay, so now this is the demonstration in the speed mode. Let us look at this also quickly. Now we will be operating this kit in the speed mode. Previously we did it in the RPM mode, now we will be doing it in the speed mode. So the first step is to ensure that the counter is at 0. That can be done by simply pressing this reset button over here. Alright, and now as the motor is already moving, we will press the push to count button, and at the same time we will be measuring the time. So We'll be taking it for about 10 seconds. Yeah. So we know this time. This is 10.36 seconds, and the number of counts registered is 1653. With the help of this, we are able to calculate the number, we are able to calculate the speed. Okay, I hope you enjoyed that as well. So, at the same voltage and RPM, we have got the number of counts as 1653 and the time as 10.36 seconds. And using that, we obtain the speed to be 2840 millimeters per second roughly. And if we use the calculation from RPM, we obtain a deviation and we get 2745.65 millimeters per second. So the error here is roughly 100 millimeters per second, but that's just 3.44% relative to the actual speed. And the reason for this was already discussed as human error, as we are doing everything manually here. So there is a higher chance of error here. Okay. So here we've got a bunch of sample readings, and what is important to observe here is number one, we've got a linear relationship between the motor voltage and the display RPM. I'll show the graph on the next slide. And the other important things are that we've got a correspondence between the multiplier output frequency and the display RPM. Okay. And also there is a strong correlation between the speed measured in both modes of operation. They are roughly the same. Okay. So now here is the graph. As we can see, there is a linear relation between the motor voltage and the display RPM. And we also observe a consistency shown in various modes of operation. So this is enough proof that this unit is a good device for speed measurement. Okay. So now let us briefly discuss some applications of this principle. Okay. So the broad application of such units can be described as non-contact motion detection. And in this case, we basically built a non-contact tachometer. But motion does not comprise of just rotations. We can use them to detect other forms of motion, for example, oscillations and vibrations. Alright. This principle is actually employed in various electric instruments like electric guitars, as you can see, where these pickups basically register the vibration frequency of guitar strings, and it goes through a whole amplification and signal processing process before finally being output as audio. So this is one of the applications. As a guitarist myself, I understand that this is the principle being used. And so with this, we come to an end to the presentation. I would thank you all, and I hope you guys have a wonderful day ahead.